Welcome back, everyone. This is part 6 in our series on contextual word representations. We're going to be talking about practical fine-tuning. It's time to get hands-on with these parameters we've been talking about. So here's the guiding idea. Your existing architecture, say for the current original system in bake-off, probably can benefit from contextual representation. We've seen that in many, many contexts in NLU these days. The notebook fine-tuning shows you how to bring in transformer representations in two ways. First, with simple featureization, and then with full-on fine-tuning. And I'm going to talk about both of those in the screencast. The heart of this idea is that by extending existing PyTorch modules from the course code distribution, you can very easily create customized fine-tuning models with just a few lines of code. And that should be really empowering in terms of exploring lots of different designs and seeing how best to use these parameters for your problem. I just want to mention that really and truly, this is only possible because of the amazing work that the Hugging Face team has done to make these parameters accessible to all of us. So let's start with simple featureization, and actually want to rewind to our discussion of recurrent neural networks and think about how we represent examples for those models. In the standard mode, we have as our examples lists of tokens here. We convert those into lists of indices, and those indices help us look up vector representations of those words in some fixed embedding space. And the result of that is that each example is represented by a list of vectors. And that's important to keep in mind. We tend to think of the model as taking as its inputs lists of tokens and having an embedding. But from the point of view of the model itself, it really wants to process as inputs lists of vectors. And that's the empowering idea, because if we use a fixed embedding, of course, then these two occurrences of A will be the same vector, and these two occurrences of B across examples will be the same vector. But the model doesn't really care that they're the same vector. We could, if we wanted to, convert directly from token sequences into lists of vectors using a device like a BERT model. And that would allow that A in the first position and A in the third could correspond to different vectors, or B across these two examples might correspond to different vectors. That would be the contextual representation part of these models. And again, from the point of view of the RNN, we can feed these in directly. That's straightforward. This is a complete recipe for doing that using the SST code and the PyTorch modules from this course code distribution. So you can see that beyond the setup stuff, which we've done a few times, the feature function is just going to use BERT functionality to look up the examples indices and then convert them into vector representations. And here, as a summary, we're going to use the representation above the class token, but lots of things are possible at that point. And then when we have our model wrapper here, we set up a torch RNN classifier, and there are just two things of note. First, we say use embedding equals false, because we're going to feed vectors in directly. There's no embedding involved here. And we also don't need to have a vocabulary. You could specify one, but it's not involved because fundamentally, again, the model deals directly with vectors. And then at SSD experiment, you again say vectorize equals false. And that is a complete recipe for bringing in BERT representations with the standard RNN. This isn't quite fine-tuning though, so let's think about how we might get added benefits from actually updating those BERT parameters as opposed to just using them as frozen representations inputs to another model. What I'd encourage you to do is think about subclassing the PyTorch modules that are included in our course code distribution, because then you will be able to write code just that oriented toward your model architecture, and a lot of the details of optimization and data processing will be handled for you. This is, I hope, a powerful example of that. It comes from the tutorial PyTorch models notebook. It's a torch softmax classifier, and the only thing we have to do is rewrite this build graph function to specify one single dense layer. We are using as our base class the torch shallow neural classifier, which handles everything else about setting up this model and optimizing it. If we wanted to go in the other direction and instead fit a really deep model, we could again begin from torch shallow neural classifier and rewrite the build graph function so that it just has more layers, essentially. And then what's happening in this init method is we're just giving the user access to the various hyperparameters that they could choose to set up this model. Finally, here's a more involved example. This one, we start with a PyTorch NN module, kind of all the way down at the base here. This is a torch linear regression model. We set up the weight parameters here, and then we have the single forward pass, which corresponds to the structure of a simple linear regression. Now, for the actual interface, we need to do a little bit more work here. So we set up the loss so that it's appropriate for a regression model, as opposed to the classifiers we've been looking at up until now. Build graph just uses the NN module that I showed you a second ago. We need to do a little bit of work in build dataset and rewrite that so we process linear regression data correctly. And then we do need to rewrite the predict and score functions to be kind of good citizens of the code base and allow for hyperparameter optimization and cross-validation and so forth. But that's again straightforward, and fundamentally for predict, we're actually making use of the base class's underscore predict method for the heavy lifting there. And then score, of course, is just moving us out of the mode of evaluating classifiers and into the mode of evaluating regression models. That's all you need to do. And again, conspicuously absent from this is most of the aspects of data processing and all of the details of optimization. The base class Torch model base here has a very full-featured fit method that you can use to optimize these models and do hyperparameter exploration. And that brings us to the star of the show, which would be BERT fine-tuning with Hugging Face parameters. Here we'll start with a PyTorch nn.module. We load in a BERT module, as we've done before, and make sure to set it to train so that it can be updated. And then the new parameters here are really just this classifier layer, a dense layer that's going to be oriented toward the classification structure that we want our model to have. The forward method calls the forward method of the BERT model, and you get a bunch of representations. There are a lot of options here. What I've decided to do is just use the Hugging Face pooler output, which is some parameters on top of the class token, as the input to the classifier. And when we optimize this model with luck in a productive way, not only will these classifier parameters be updated, but also all the parameters of the BERT model that you loaded in train mode. The interface is a little bit involved here. So what we do is provide the user with some flexibility about what choices to make. Build graph, again, just loads in the module that I showed you just a second ago. And then build the dataset is a bit involved, but what we do fundamentally is use the BERT tokenizer to batch encode our data. And then we do a little bit of processing on the output labels to make sure PyTorch can make sense of them. That's really it. And the heart of this is just that we're again using Hugging Face functionality to represent our data to the BERT model. And then this is the really interesting part. Calling the forward method and then fitting the classifier on top is pretty much all you need to do. And of course, that opens up a world of options. Reps here has lots of other things that you could use as the input to this classifier layer. And many of them actually might be more productive than the simple approach that I've taken here.